Should we start now? Yeah. Good afternoon, everyone. So yeah, my name is Sean Lu from the ByteDance System Technology and Engineering team at the US. So I represent, my colleague Zijian. He's not here. So yeah, I mainly presented here. Also, our research development is like, advised, direct, by John, Professor. So yeah, special thanks for the John. Yeah. So here's today's agenda. So we will Homa congestion introduction. I think John already did some, so I can't quickly go through that. And also we will talk about Homa. So we mainly look into Homa for our improved RPC transportation. So we will talk about the limitation of Homa in RPC context. Then we will, to address some of the limitation, we'll go into the congestion control enhancement. And also we do a little bit RPC streaming enhancement. So then later we will do the performance evaluation and, give our conclusion and, future improvement on that. So yeah, first, today, at the RPC world, so at the data center, mainly TCP is the king. So widely used, supported. But it has, high latency on the short message, especially in mixed workload. And then, RDMA, right? That's, very with the high throughput and the low latency. So everything is good. So only limitation is it has limitation on the number of concurrent connections. So, depend on which kind of NIC you have. So, and especially on the mesh network, there are some limitation. The scale can go big. So also it needs RDMA capable network and the switch. So that is kind of, expensive. So we look at the alternative solution like Homa. It provides high scalability, low latency, and also high throughput. So that's basically in between. And yeah, I think I don't need to go through this. Only thing is it's a message-based, connectionless protocol, and also implement a unary RPC. So it's pretty very much match with our application in RPC land. And it is a receive-driven control protocol. So it's like a divide unscheduled byte, scheduled packet. So usually the unscheduled packet go first, reaches the receiver, and then it need wait for the client, then can send out a scheduled packet. So usually receive know all the information, it can do the schedule. So one thing is usually, right? So for this unscheduled packet, it is currently it's a fixed window, so it can go big. And for the 100 gig network, it can go about 100K something, right? It's yeah. So and on the client side, so it's mostly also 1 to put RTT byte for each send. So to schedule the bandwidth. So that's also related to this. So it can be a larger. So it's I think pretty much not that flexible in this now. I think John has recent patch. I think you probably address some of this And also, there is overcommit. So for each send, it will overcommit the link, essentially also based on these, RTT bytes. So there is maximum overcommit about 8. It's like, this is according to the privilege level the switch provide. So there is potential, right? Buffer could build up to the overcommit. And on the send side, there is SRPT. So essentially, for each send, if there are concurrently multiple RPC messages, so shortest goes first. And also, there is a pacing, can pace the speed, how, you put it on the wire. It is based on Nick's backlog. So then, come to what we see, right? So we tested this. So it's like, one thing is inefficient pipeline for larger messages. So Homa message-based interface, which ensuring complete message delivery. But there is a pipeline. So because it needs a whole message to able to deliver to application, then it can read from the kernel to the user space. So the throughput is affected by that. So we measured also, the gRPC over Homa. That our sweet point looks like it's like 50K message size. So above that, TCP performance is like bad. So essentially, if you look at a single size message, even the latency will be come close, even bigger than that 100K TCP. Well, looking better even on the latency. So, but for the mixed load, the Homa always kind of beat the TCP on the, P99 messages. So another thing we come close is like, because of the non-standard socket API interface, it's a little bit hard to migrate to different RPC framework. So we, in our company, we are using the, Swift gRPC, and we also have our own byte RPC framework. So it is a little bit a challenge too, because on the upper level, it doesn't see, right? So RPC ID, Homa ID. So we have the different channel, and it's like persistent, because everything is designed for the TCP. On the upper level, all the interface, it's assuming there is a persistent, connections, right? That at the transportation level, it actually not looking into the RPC ID. It has the string. So we somehow need to map that string to the IP. So that's one challenge, right? So another thing is, because TCP has concept of long life RPC, long life connections. So Homa doesn't, Homa for Homa is like request, response, that's done. So it will have some little bit overhead, create and reclaim, and So there is a window challenge. So for the unscheduled byte, so for the Homa congestion control, right, it is actually sensitive to these RTT byte, the unscheduled window config, right? So what we work with is maybe not recent, but what we see is only one RTT config. So in reality, right, there is a uniform network. So essentially, to every different peer, these will be different, actually. So that need to be improved. So, and also we for congestion control. So if RTT actually is bigger than 2 microseconds, because this window, so the congestion control kind of, a little bit weak, and it might invite in cost congestion. So later on, I will talk about that. We do the test. So yeah. So if you make this RTT byte low, then it will not cover the RPP. So there will be cost of the downgrade throughput. And other thing is like this RTT is like on the unscheduled window, scheduled window. So we are mostly use the similar value. So we need to separate that out, right? So probably need a dynamic adjusted window. So it's like for that. Another thing comes up is like when we tested Homa, right? So we kind of use the production environment. So they are always have TCP traffic run on the CN switch, the AB port. So we cannot avoid. So those two will coexist. So what could that be, right? Because everyone have its own congestion control. They are not aware with each other. So that could be an issue, right? So that we will do some experiment to test out what will that problem will cost. So another thing is like if unscheduled packet is big, there might be some encasting will cause the buffer buildup. So yeah. What we do is like, so we do a little bit enhancement on here. So we kind of, add dynamic per peer RTT detection. So what it do is determine the minimum RTT between the different link, different peer. So you can automatically decide how much window based on that you want to put on the unscheduled window or grant window based on that. So also, apply, you leverage RTT delay to get sense of the, congestion detection. So based on the RTT delay of each peer, and then we can adjust the window based on the congestion level. So that is what we, so our enhancement, so this is like, you can adjust for each one peer, right? So on the incoming Homa soft IRQ level, can send out RTT probe message, right? Those is on the, between two Homa transportation on the different peer. So when the peer receive that on the soft IQ level, it can just send it back. So that way, we try to get a sense of, what is the latency between these two? Because this is the shortest message with the highest priority. So we use this to determine the minimum RTT between those two peers. So one thing is this, like RTT will be fluctuate, but RTT mean, this one, over time, it will get stable. So you can use this as reference. So how much, RTT delay will be between those two. So this is kind of indicate, right? Then, when you detect the current RTT recent, right? So if it is like compared to this, is multiple times big, you pretty much know there is some congestion going on there. And also, what we do is just very simple, because more sophisticated algorithm we can add late. But for now, according to our experiment value, it's pretty much 8 times of the RTT main. That's definitely there is congestion. So yeah. And also from the scheduled window, right? So we kind of do some experiment to decide, okay, for the scheduled byte, we want to put more on there. So essentially, it will be 3 times RTT main. So we can use, so for per link per peer, so we would use a little bit larger window for that. And also we can reduce the overcommit, right? You can give a little bit big window to one cent, but less overcommit. So that will be less severe on the in-cast case. And from the send side, we can do the adjust window. So this one is typically, so if there is no congestion, we will put 2 RTT main as a window to decide how much for the initial window. So for the Homa, it's you first get to the desired unscheduled window. That's usually a little bit big. Then if there is congestion, so it enters in congestion avoidance earlier, right? So that window will be reduced to, so until if it detected congestion, you can use the minimum, pretty much a GSO size to send that out. So that is kind of adjustment here, right? So also, unscheduled ratio, we actually on the receiver side, pretty much it knows how much incoming data it has. It will come to this receiver. So it's pretty much get some kind of indicate to, for the next, RTT time, what the traffic is going to be. So currently what we do is okay, so on the send side, we kind of more active doing. So if we see this unscheduled ratio is less, that means there are quite a lot of scheduled byte already, granted, assigned there. So, and also if there is no, on the send side, I have nothing to do, right? Slot list is if it is not empty. If it is empty, we still follow the same unscheduled byte. If already there is some grant byte there and a scheduled byte, we need a schedule on the wire. Also, there is unscheduled byte. So we can cut that window in half in that case. So what it turned out is for each send, it's only first one will have a big scheduled window. For the, whatever concurrent RPC, it will reduce to a smaller window in that sense. So that's for the small enhance on the congestion side. So what other thing we do is we want do some Homa IP streaming enhancement. That the purpose is more so we provide option, right? So originally for the streaming, right? Each streaming, if you have the 8 RPC, so it map to the Homa RPC, actually each one will create its own RPC, so it will create, destroy, create, destroy. This is one thing. So there is a little bit overhead there. Another thing is we want to create something, it's more persistent RPC, so can map to the TCP, long-lived, connection, right? So in that case, easy to, for migration porting. So that's another purpose. So what we do is we map the Homa RPC ID actually into the string. So Homa ID, RPC ID, you can, in the same RPC, you can actually have a sequence of RPC. So running on the same Homa RPC. So that mainly for us is two things. So once is a porting, another thing is we want to have, for example, you have a very big package, right? Messages, because they are still challenging for big messages. So especially for the ByteDance, right? So we have some message that could be, like 10 meg something, for the RPC, so streaming. So we use that very often. So there is quite a lot of user case for big RPC messages. So that's the thing. We want to have this kind of enhancement. And then we talk about, for those, we have the test setup. So we have a 25 gig network. So mainly Intel CPU and 500 gig RAM, and we also start the VM on top of that, use SIOV, and we have 25 gig Tor switch and also 100 gig network. So that mainly to see, on the different network, what will be the performance, and we also use the load, on the, the PAPE, John's PAPE, so that's W2 to W5. This is for mixed load. And also, use the CP node, the John write to, so this can compare the performance with the Homa and the TCP and with the different parameters. We can pass in the workload and, how many concurrent, a client max and how much port we use. So, and this basically is for basic setup is for, one VN on the server side, one VN on the client side, different host use SIOV, they connect through the Tor switch. So that's the application. So from performance wise, so with the optimization, we pretty much see, right, from the 20K to 500K. So there is the throughput improvement for the modification one. So it's about 5 to 18% on 25 gig, network. And for the latency wise, they are pretty much similar case. Oh, this is for 100 gig. So for the 500 K size, it kind of improve like 15, something like that. So it's mainly applicable to the larger packet, RPC packet. So, and the latency wise, it's kind similar. A little bit better, but it's similar. So with the two cases. Oh, here, right, you see the W5 case. For the unoptimized case, we actually observed the buff overrun because of due to for the W5 workload, that is average size 380K, but it has, very large, packet, on the there. So actually, with these 4 is, concurrently 4 W5 load, run on top of that we see the big jump up on the P99, but with, at just the window, it's able to avoid that. And we also do the in-cast test out to see whether, the buffer case, how it will be, right? With 621, in-cast case, and with the different packet. So it do happening on the W5 in this case, right, for the latency, case. So, so with, actually with 25 gig network, we don't see this problem. So only thing is with the, 100 gig, you have more bandwidth, right? So it need to allocate a more larger window for unscheduled byte in that case. And we also test the split traffic. So in this case, there is both Homa's traffic and the TCP traffic. What we do is like, we first start 3 TCP nodes across this network. So with the TCP server there, so it will be about, above 40 gig traffic already run on that. Then we start the Homa, add the Homa traffic on top of that to see what happens. So how it affects the throughput, how it affects the latency, right? Because they are using different, congestion control, and the Homa is assuming, okay, I own the whole the bandwidth. So TCP is assuming, okay, whole bandwidth is TCP. So let's see, right? So this is the one for the 100 gig. So we split traffic, right? So actually, not that bad. So if you look at, so originally, without Homa packet, TCP actually, I just said, a part of about the 50 gig, throughput there. So then we add, like, Homa traffic about, in this case, right, 40, like 30 gig Homa traffic on that. Actually, TCP still have the same kind of throughput. So it doesn't affect, actually combine those two, you get more throughput. This is actually is good, right? So they doesn't conflict the traffic that much, so in that case. And also, with the optimized one, it actually able to detect there is TCP traffic. So it split, emit less traffic on the Y. So it get less throughput than the vanilla Homa. So in this case. So then we look at the latency, right? So latency-wise, vanilla Homa also see that P9090 issue because of the larger window, and for the latency, both are actually on the P50, right? Both sides a little bit. It's like two times higher than before, and also. So if you look at the W4 traffic, that's mainly for the mixed traffic, but the size, average size is about 60K. So the P50 is still decent on the Homa side. So you get the 67, right? This is kind of full load. So you get that, and the P99 about 700. So that means we don't need to worry much about, you put the Homa traffic and the TCP traffic on the same port. So one thing I need to notify, say is this, right? When we doing the test, actually TCP and Homa traffic, they are through different VF, SIOV. So they don't share the same VM. So that's kind of a little bit split at that. But on the switch side, they are shared. So they are shared the same port. So that's pretty much, remove our kind of, concern, because usually if we want to deploy Homa traffic, there definitely will not be that much, right? You don't want to have the congestion TCP, heavy load on the same port. So we will allocate that. At least this is at least a concern to us. And the conclusion is like, RTT detection algorithm actually works effectively in our case. So it's also reliable. So it works on the 25 gig, 100 gig. So it plays nicely. And, adjustable window able to gain 5 to 18% throughput. So that means, pretty much we can optimize on the receiver side. So for optimize through the adjust window to give more like grant, bigger grant window to, gain more throughput probably in the future, right? So, and the buffer overflow resistance. So algorithm able to demonstrate resistance against buffer flow. And also, compatible with the TCP traffic. So that's the conclusion we get. And then what is next? So next we want to, so like to see, right, whether we can get a more accurate RTT measurement. Another thing is like, can we base the congestion on the average RTT deviation? Also, another side, we notice whether we can optimize the piece at the center side, because we still notice the traffic pattern is kind of, a little bit burst, both for TCP and Homa, right? So if that can be optimized to gain more throughput, also, zero copy is one thing, right? So probably will address the larger packet throughput issue. So I kind of, we want to work with the, Professor, John, to see whether we can, get more on that, on the throughput side. Yeah, this is the reference thing. Yeah, it's pretty much. So, questions? John.
So this is very interesting, but I want to go back to something that John said for a moment. The point that TCP is a stream-based protocol. Mm-hmm. However, things like RPC are not stream-based, they're message-based. Well, it turns out if you look at TCP applications, almost all of them are message-based anyway. So what we do is we put messages over TCP, mm-hmm. and then we deal with that. So we did this thing a while back called kernel connection multiplexer. Mm-hmm. Are you familiar with that? Mm-hmm. It's an N-to-M multiplexer. And the way it works is on the top we have these things called KCM sockets. And they're sock-seek packets, mm-hmm. which is the type. So they're not the normal datagram nor stream. the socket packet's kind of cool. It is a message-based socket type, but you can also read the message in parts. So if you're like reading a 15 megabyte message, you can read it 64K at a time. It's perfectly fine. So it's a really good interface at the north end for kind of getting messages out of the kernel. And if we combine that with the zero copy techniques, then we could have a zero copy instantiation of that. So I think that might address some of that sort of techniques there might address some of the top end API. But at the bottom end of the multiplexer, what we did was we allow some number of TCP sockets to connect to this thing. And they could be from different peers, or they could all be from the same peer. But they have this interesting property that I just thought of in context of this talk. A sender, say if a sender had multiple connections to a receiver, it could actually send different messages in parallel, and they could be different sizes. And it could use the same technique. So we can actually interleave the messages like you were mentioning, John. And that the receiver, because if they're on different connections, we would actually assemble the messages per connection, which would kind of give you the same effect of Homa, because now we could have one big message that's in flight on one connection, one little message, and that little message finishes, then we send it up through the multiplexer. So I don't know how much of that maps into Homa, but in some sense, it actually could be like a pseudo Homa.
So that means, you know, you pretty much do more work on the RPC framework side. So it's like you pretty much need to do all these in the application level for one thing, right? So thing with the TCP is like this. So like KCM you mentioned, right? So if the connection get lost somehow, right? So they always have the retry issue, especially in our, you know, we see a lot of this issue on the, you know, RPC. So once it gets into the congestion, right? So it will time out. Then, you know, everybody, okay, go, they connect, right? So that is connection-based issue, right? So with the Homa, this problem ultimately go away.
It is and it isn't, because if you're striping across multiple TCP connections, you could kind of view those as independent, and they'll have independent congestion control. Anyway, it might be something to look at. The other thing that was kind of cool about that is we used eBPF, and I was thinking for something like steering RPC replies to the right socket or the right queue. eBPF could be really good at that. It's an easy way to do this without modifying the kernel. Of course, you know, we want to not have to modify the kernel, but it could be very dynamic. So something like the congestion management probably would have to be in the kernel. But some of the other stuff around the interfaces and the API, there might be some nice pieces you could reuse without having to kind of reinvent all that stuff.
You kind of, you know, have the different RPC message go to the different connections, then tail of line problem goes away, right? That's the strategy. Yeah. So, but it's kind with, you know, what layer you want to play, right? With that, you know. So what we are actually looking at from our side is like we want to actually, if you know, refine, you know, the Homa, right? Make it dedicate RPC transportation. So do a lot of, you know, to application. We are simple. So we just send message, get the response. That's all. We don't need to, you know, take care rest of them. That's probably beauty of the, you know, dedicate RPC transportation, right? So all the other issues, someone take care for it. It's RPC specific issue. Because TCP, it's not, you know, specially for RPC, right? So if we look at the RPC framework, gRPC, very complicated, a lot of code. Actually, John mentioned, right, with the gRPC, that latency goes up a lot. So that kind of thing is like, those latency, which level of take that cost. For example, like with the higher bandwidth, with like 200 gig, 500 gig. So later on, software latency actually is a main issue. It's not a network optical thing, right? So that may demand thin layer of RPC framework. Yeah, so that's, I think, that's also, probably we can think about, whether we need a dedicated RPC transportation in the kernel.
Well, yeah, I mean, think about it this way. So layering, always a good idea in principle, obviously.
Yeah,
Sometimes
yes.
we want to munch layers. But RPC, it's pretty clear, right? If you divide it in the transport versus the RPC processing, that's a good first division. And usually, yeah, we want to split that. We kind of know what we want in user space. We kind of know what we want in the kernel. RPC is kind of unique because the actual thing the application wants to deal with is the message, not a whole bunch of bits. It doesn't care how it got that message. It just wants the message as quickly as possible. So if you kind of start with that abstraction, then what that leads you to, and I hope an outcome of this work is there are multiple levels of this problem, and hopefully, like anything else, any sort of kernel development, we'll make innovations, and then it'd be great if we could apply those innovations to a slightly more general problem. The zero copy, I think, is a great way. I think this is, we have a good source, a good way to do zero copy here. Maybe it's applicable here. Hopefully, it'll work the other way. So as you're figuring out some of these properties of RPC with this new protocol, feel free to suggest those back into the other common cases of TCP and what have you. Then we all benefit. So
sure.
That's why I like work like this, especially if it's coming out of academia, because even if this work doesn't directly translate into something that's deployed, almost certainly we'll get a lot of good input and feedback, like you're presenting here. So it's why it's exciting to see stuff like this.
Well, a couple comments. First, thanks for your comments about that. The problem I've seen is that messages and streams are really like oil and water. It's if you have streams underneath, it creates all sorts of problems for trying to layer messages on top. You suggested like using multiple streams to get something SRPT-like, and you can do that. But it is really challenging that stream API just puts this hook in your gut that limits in lots of different ways, unfortunately. Then also, I just wanted to thank Xiaochen for all your great measurements. You've pointed out a bunch of problems with Homa that clearly need to be addressed. Until recently, I've been doing all my work on 25 gig networks because I just haven't had access to 100 gig network until recently. And as you pointed out, there are a bunch of issues when you ramp up the network speed that stress the current Homa implementation. I think the biggest one is the window management.
Yes.
We need to find some ways to have much larger windows at high network bandwidths. TCP does this naturally. It will just scale up the window size until it either gets happy or something breaks. And Homa has had more of a fixed size window, and I think it's going to need to have something a little bit more flexible in the future.
Yeah, so I think, another thing is Homa on the receive side have more knowledge about what's going on. So it will able to do more predictable prediction of the traffic. So that will keep the traffic more in control. So that's I think, in the future, probably.
Yeah, congestion control is all about how much information you have.
Yes.
If you don't have much information, it's pretty hard to do a really great job at congestion control. You will pay one way or another for it. Even Homa nobody can have perfect information in a distributed system. All the information you have is at least one RTT out of date. But Homa, because it has messages, the message sizes convey a lot of extra information. You know how long this message is going to be and when it's going to end. And that's information that a streaming protocol, for example, doesn't have.
Yeah. Hi. Thank you for the talk. So you mentioned RDMA.
Yeah.
and its scalability issues. So it has a certain
Yeah,
threshold
it
beyond.
on what kind of RDMA car you have.
Right,
like,
right.
Yeah.
And you also have vendor-specific extensions,
Yeah,
which adds more.
specific. So we always for HPC, some of the network you are willing to put a bunch of money there. Some of them,
Right.
so they are always something in the middle, right? So if it can use the generic software solution, so why not, right?
So my question is, if you manage to do any tests before with RDMA before getting to that scalability limit?
So our have RDMA network. So usually we do 2 hops. So so for the node near closely, the network very, put the very closely. So you can do the RDMA. So there is extra hop in between, right, on the different port, especially for the container case. So you need to kind of have TCP in the between, do that thing, converge, because that to, so aggregate the traffic, then deliver to the, RDMA network. So RDMA network just play, it's
So you mean like RDMA
you
connection
need
management?
low latency,
Or?
Close by, so So the topology, right? For example, you cross-lag, so the latency gonna be good, big. Very different. It's also, you need to be very simple network there. So it's not
True, okay.
not
And it's also a
magic.
bit comparing like
Can't
apples
just,
to oranges, I guess.
But the RDMA there, all the problem gone. It's not magic.
No. Okay, thank you.
Okay.
One more question online. Tian, do you want to come online, or you just want me to read the question?
Okay.
Okay, I'll just read it, or you can read it, Mister. Okay, the numbers are super exciting, he says, but he asks if vanilla Homa here means Homa without any parameter tuning. For example, there's nothing in ins mode when you load the module, or do you have anything in ccTL?
Okay. So for the Homa, right? Homa you can just compile currently, right? Out of the kernel, then you can just load it. So that's it. Actually, dependency, like with different version, you only need a little bit change there. So it's very easy. So what we do actually on our test, we kind of build with our own kernel, right? We also optimize even the TCP side. We also have the whatever the ByteDance kernel. So there is TCP patch optimization. We also put in the same kernel. That will be a fair compilation, right? So, and for the vanilla I mentioned, it's like, with the sys control one, and, we have the RTT byte config. So the optimize is based on the, minimum RTT detection. So that we call the optimized one. So you don't need to do the config in that case. So it's like each different link peer, it detect by itself. So that helps deployment. So you don't need to test the network to find out, okay, what value is good, for this network. So
Actually, maybe I can also take a stab at that question. The answer is I'm embarrassed to say that the default parameters that come when you install it are not much different from random. They're not useful for any actual system. I don't know why it ended up this way. I'm working on having first, to make the defaults better. Second, I've been building a script that will kind of adapt itself for various systems to make it easier to configure Homa. But right now, you do have to do some parameter tuning to set it up for your system.
Yeah. So
I apologize for that. That's just a bad thing that I haven't fixed yet.
okay. Okay, thanks.
Thank you.